Isentropic steady flow devices. How do we define the efficiencies of devices such as turbines, compressors, and nozzles? Let us start by talking about how we would go about selecting a turbine. We have a combustor and we want to use the hot gases from this to drive a turbine. So we can attach a turbine to it. We would take the high pressure fluid from the combustor, pass it through the turbine, which would do work on the surroundings, and low pressure fluid would leave the turbine. We want to know what is the maximum work that we can get in theory from the turbine. What information do we have that we can use for analysis? If we have the combustor, we know its pressure and temperature. So at the inlet to the turbine, we have two properties, P1 and T1. At the exit of the turbine, if we are exhausting to the atmosphere, we know the pressure. But to fix the state, we need at least two independent properties. So we need one more property. What property can we use? We want to calculate the maximum work possible. So let's assume that we have an ideal turbine. A turbine is well insulated, and so typically heat losses are low. Let us assume that the turbine is perfectly adiabatic. We are also going to neglect all frictional or other losses in the turbine, which means we are going to assume that it is reversible. If the turbine is adiabatic and it is reversible, we know that this means that it is isentropic. We have an isentropic turbine. At the inlet, we know the pressure and the temperature, P1 and T1. That means we can calculate what the specific entropy is, S1, which is a function of P1 and T1. At the exit, we know P2. But if we assume that the turbine is isentropic, then the entropy at the outlet, S2, is equal to the entropy at the inlet. So this gives us two properties at the outlet, the pressure and the entropy. And this is enough information to fix the state. We can now calculate all the other properties at the exit. It is convenient to represent expansion through an isentropic turbine on a TS diagram. But before we do that, we need to know what an isobar, a line of constant pressure, looks like on a TS diagram. For an ideal gas, we know that delta S is equal to Cp ln of T2 upon T1 minus R ln of P2 upon P1. If pressure is constant, as it is along an isobar, P2 is equal to P1, and the second term, ln of P2 upon P1, goes to 0. We can therefore rearrange that equation to say that T2 upon T1 is equal to the exponent of delta S upon Cp. The temperature is therefore increases exponentially as the entropy increases. On a TS diagram, a line of constant pressure will look like this. Now this is the line at some given pressure, P1. At a different, higher pressure, P2, the line would look like this. And we can confirm this because if we go back to our equation of delta S equals Cp ln of T2 upon T1 minus R ln of P2 upon P1, if we hold the entropy constant, the left-hand side of that equation is 0. And we can see that as the pressure increases, the temperature increases. Therefore, the isobars will be a series of curves which look like this, and we can see that as the pressure increases, the lines will be higher and higher. We can now show the isentropic expansion on a TS diagram, where the gas expands from some pressure P1, which is the inlet pressure, to P2, which is the exhaust pressure. If the inlet temperature, T1, is fixed, that fixes the inlet state 1. The isentropic expansion is then a vertical line on the TS diagram, And this fixes the exit state to S. We write the S to remind ourselves that this is an isentropic process. This therefore fixes the exit temperature, T2S. The inlet entropy, S1, is then equal to the exit entropy, S2S. The work done by the isentropic turbine, W dot T, S, is equal to m dot times H2S minus H1. If we assume that the specific heat of the gas is constant, we can write this as m dot Cp times T2S minus T1. This is the theoretical maximum work that we can get from the turbine. We can also show an irreversible expansion for a real turbine on the same TS diagram. This is what an irreversible process would look like. The entropy at the exit, S2, is going to be greater than S2S because there are irreversibilities during the process. Because the isobar has a positive slope, the temperature T2, which is the actual temperature, is going to be greater than T2S, which would have been the exit temperature for an ideal turbine. The work done by an irreversible turbine, therefore, W dot T, equals m dot Cp times T2 minus T1. This is the actual work output. The ideal work, which we had just previously calculated, W dot Ts, is equal to m dot Cp T2S minus T1. Now we can see from the diagram that T2 minus T1 is less than T2S minus T1. And therefore, the actual work, W dot T, is less than the ideal work, W dot Ts. We can now define an isentropic turbine efficiency. The turbine efficiency is defined as the actual work output divided by the ideal work output. The efficiency is denoted by the Greek letter eta, and we put a subscript T for turbine. And this equals W dot T divided by W dot Ts, which equals H2 minus H1 upon H2S minus H1. Since the actual work output is always less than the ideal work output, the efficiency is always less than 1. For turbines, the efficiency typically lies between 70 to 90%. We can define the efficiency of a nozzle in a similar way. Here we have a nozzle, and the fluid is going in at velocity v1 and it's coming out at velocity v2. We assume that v2 is much larger than v1, and therefore we can neglect the inlet velocity, and we are assuming that v1 is approximately 0. For an isentropic nozzle, the exit velocity would be some v2s. For a real nozzle, the exit velocity would be a lower value, v2. We can therefore define a nozzle efficiency as being the actual kinetic energy at the exit divided by the ideal kinetic energy at the exit. The efficiency, therefore, would be v2 square divided v2s square. We can compare the work supplied to an isentropic compressor with that supplied to a real compressor on a TS diagram. This shows the compression process from an inlet state 1, where the pressure is P1 and the temperature is T1. It is compressed in an isentropic process so that S1 is equal to S2S. The final state is represented by 2S, where the temperature is T2S and the pressure is the exhaust pressure, P2. This is the compression process for a real compressor, where the process is irreversible. So the final state is S2, where the entropy is greater than S1. The final temperature is T2, which is higher than T2S. The work supplied to the isentropic compressor, W dot C, comma S is M dot H2S minus H1. The work supplied to the irreversible compressor, W dot C, is M dot H2 minus H1. And we can see from the diagram that H2 minus H1 is greater than H2S minus H1. The irreversible compressor therefore requires more work to be supplied to it than the isentropic compressor. We can therefore define an isentropic compressor efficiency, and this is defined as the ideal work supplied divided by the actual work supplied. Note that this definition is the reciprocal of the definition that we had given for the turbine. We define it this way so that the efficiency will always be less than 1. The compressor efficiency therefore is W dot C, comma S, the ideal work, divided by W dot C, which is the actual work. This equals H2S minus H1 upon H2 minus H1. Typical values of the compressor efficiency lie between 75 to 85%. To summarize, assuming isentropic flow gives us one property to fix the exit state of flow devices. A turbine efficiency is defined as the actual work output from the turbine divided by the ideal work output. A compressor efficiency is defined as the ideal work supplied to the compressor divided by the actual work supplied. A nozzle efficiency is defined as the actual kinetic energy at the exit divided by the ideal kinetic energy at the exit.